Next topic is relative motion of two particles. In the previous topic we assumed the quantities, the kinematic parameters, velocity, acceleration and position in the absolute sense, and we use a single reference system. Sometimes the analysis becomes easier if we consider the relative motion. That is, we define the position vector, we define the position, velocity and acceleration in the relative sense using two or more than two frames of reference. For example, we consider a relatively complicated case. Suppose there is an airplane which is moving and it contains a propeller. At the location on the propeller or the particle on the propeller, we have to, for example, determine the kinematic parameters. So the kinematic parameters of that particle which is on the propeller, and the propeller is rotating in a moving airplane, it can be described in a suitable or easier way if we consider the relative motion. We can divide the complete motion of the particle on the propeller into two components. One component is the motion of the airplane, and second component will be the motion of the or rotation of the propeller with respect to the airplane. To determine the motion of the particle on the propeller, we will add the two motions in the vector form. That is, we will add the circular motion of the particle or propeller with the motion of the airplane. So for that we need a moving reference system. In addition to the fixed system, we need an additional system which is moving. So there is a primary system which is fixed, and there is an additional system which is moving. The primary system is the fixed reference system, and the fixed reference system is assumed to be attached to the surface of the earth. Even though the earth is also moving, it has some angular motion, but since the velocity of the motion is very less, it can be considered insignificant and it can be ignored. The relative motion terms can be expressed in terms of coordinate system. You have studied three coordinate system. One is rectangular, normal, tangent and polar. So for the earth motion, we can neglect and we can analyze the motion of a particle with respect to the fixed system and with respect to the moving coordinate system. The fixed system is considered to be attached to the surface of the earth, and earth is assumed to be stationary. Now suppose there are two particles A and B and they are moving. There is a fixed observer and the fixed observer is attached to the fixed system. The position vector with respect to fixed observer of particle B is RB, and the position vector for particle A with respect to the fixed observer is RA. Now for determining the position of the particle B, we can have a relative system. RB can be defined in terms of RB/A. So in vector form it will be RB equal to RA plus RB/A. So RB/A is position of B with respect to A, and in the present condition we are assuming that there is a moving reference system or translating reference system, and that translating system is attached to A. So we can define the position of B with respect to the translating observer. So here we have two coordinate system, one is x, y, z, and other one is x dash, y dash, and z dash. So this is our vector relation RB equal to RA plus RB slash A. Now we can differentiate this equation for position. We will get the formula for velocity, that is velocity of B equal to velocity of A plus velocity of B relative to A. When we differentiate the position RB, RA and RB slash A, we will get velocity, and since position is a vector quantity, we will have an additional term for the change in unit vector. But since we are assuming that the reference system, the moving reference system, is only translating, and when the frame of reference is only translating, the direction remains same, that is the I dash will remain in the same direction as I. So we get simply VB, VA and VB slash A. We can describe in words that velocity of B is equal to velocity of A plus the velocity of B with respect to A. Again, for the translating frame of reference, the unit vectors have zero derivatives. For the rotating axis, the derivatives of unit vector are non-zero. So we will be considering the rotating axis in the future lectures, but for the present case, we get simply VB equal to VA plus VB slash A. Similarly, for acceleration, acceleration of B is equal to acceleration of A plus acceleration of B with respect to A. We can have the opposite case. It is not necessary to have the moving coordinate system attached to A. We can have the moving coordinate system attached to B. So this is a second example. Here we have the fixed coordinate system which is attached to O, and there is a moving coordinate system which is along with B, and we can define the position of A directly. If we determine the position of A directly, then it is RA, and if we determine the position of A with respect to B, then we will have RA equal to RB plus RA slash B. Similarly, after differentiation, we get the similar relations for velocity and acceleration. From the previous relations, RA equal to RB plus RA slash B, and then previously we had RB equal to RA plus RB slash A. If we solve these two, we get RB slash A equal to minus RA slash B. Similarly, the signs will be opposite. When we obtain velocity of B with respect to A, or we obtain velocity of A with respect to B, we will have same magnitude, but the direction will be different. Next topic is kinetics of a particle, force and acceleration. The chapter 12 was about kinematics, in which only the parameters such as the velocity, acceleration, position were considered, and the driving force, the reason of the motion, was not considered. When the particle is moving, there are some forces due to which it moves, and often there is some acceleration due to the action of the force. So kinetics include the relationship between the change in motion of a body and the forces that cause this change. Instead of forces, we can study the motion with the help of work and energy, and we can have the impulse and momentum. So whether we are considering directly the force, or we are considering the energy changes and work, or we are considering the momentum and impulse, all are considered within the topic of kinetics. The basic equation for the kinetics of the particle is based on Newton's second law, and the students are well familiar with this law. It states that when there is an unbalanced force on a particle, the particle will accelerate in the direction of the force, and the magnitude of acceleration is proportional to the force. Now this law is determined experimentally. It can be proved experimentally. When there is an unbalanced force, it results in acceleration. If the forces cancel out, then there is no acceleration. The object remains at rest, or it moves with a constant velocity. Okay, from F equal to ma, we can write m equal to F over a. So m is mass, and mass is like a resistance. If the mass is more, then for the same force the acceleration will be less. So F equal to ma, when mass increases, acceleration decreases. So mass is like a resistance for the acceleration components. So mass can be defined as the resistance of the particle to have a change in its velocity, that is its inertia. So F equal to ma can be written as m dmv over dt. Acceleration is dv over dt. Since mass is a scalar quantity, it is constant. We can move mass into the differential sign. So we can write the equation of motion F equal to ma equal to d mv over dt. In that case, we will describe the law as force equal to rate of change of momentum. This law is valid. The second law of equation of motion is valid for almost all the engineering applications. There are few exceptions which have been pointed out by other scientists. For example, Einstein showed that if the particle is moving with very high velocity, in that case the time is not an absolute parameter, and in that case the equation of motion F equal to ma becomes invalid. So if the velocity is very high, the equation of motion fails to predict the exact behavior of the particle. Some other researchers have found that if the particle size is very less, it is close to the size of atom, then in that case F equal to ma becomes invalid. But for engineering applications, we have a sufficient size of the particles in millimeters or micrometers to a minimum, and we have the particle of very large sizes. In that case, the equation of motion can be considered valid. Another law which was obtained by Newton was for the mutual attraction between the particles. The students are also familiar with this equation, F equal to G m1 m2 over r square. Here G is universal constant of gravitation, its value is written. M1 and M2 are the two particles, R is the distance between the centers of the two particles. So usually the force of attraction between the particles is very less, it is almost negligible. The only force of attraction which is usually considered is the gravitational force, which is between the surface of the earth and the objects which are on the surface of the earth. Because here we have the earth size is, the mass of the earth is sufficient and the distance is less, so this is usually the only force which is considered. We can convert this equation into W equal to mg. If we replace m2 as me, mass of earth, m1 is mass of the particle, then g is substituted for capital G me over r square. So there is a correction here, it is r square. So W equal to mg. The unit of weight is Newton, the unit of mass is kilogram. In SI system, in the English system, the unit of mass is slug and the unit of weight is pounds. Now we consider the equation of motion when there are several forces. Previously we wrote simple F equal to ma, but there can be number of forces on a single particle. So when there are number of forces, we have to consider the forces in the same direction and we have to add them. So in that case, resultant force Fr is equal to summation F. So general equation of motion becomes summation F equal to ma. We can consider, suppose there are two forces F1 and F2 on a single particle which has a mass of m. We can graphically draw the resultant vector, we can graphically show the direction and magnitude of the vector. Suppose there is force F1 and F2, the magnitude is proportional to the direction, magnitude is proportional to the size of the vector. The resultant force will result in acceleration. So graphically we can show the force vector and the acceleration vector in this form. When we are drawing the force vectors and the resultant, then it is a free body diagram. The free body diagram, as the students know, is the diagram which consists of particles and it shows the forces on the particles which is assumed to be free of the surrounding supports. In addition to the force vector, we have the acceleration vector. The resultant force in the horizontal direction results in acceleration in the same direction. And the acceleration vector, when it is drawn, it is termed as kinetic diagram. If the resultant force is equal to 0, then acceleration will be 0 and the particle will move with a constant velocity or it will be at rest. So this is a condition of static equilibrium. Then we have the condition of dynamic equilibrium. When the equation balances, summation F equal to Fa balances, then it is a condition of dynamic equilibrium. The next topic is inertial frame of reference. The limitation or the condition for the equation F equal to ma to satisfy is that we have the inertial frame of reference. The equation of motion is obtained for the inertial frame of reference. The inertial frame of reference is the reference frame which is non-rotating and it is translating with a constant velocity. Non-accelerating systems are termed as inertial reference frame. If the reference frame is moving or translating with a constant velocity, or it is at rest, then it is an inertial frame of reference. If the translating frame is translating but accelerating or increasing speed, or it is rotating, then it will not be an inertial frame of reference, and in that case the equation of motion will become invalid. So if the observer does not accelerate, from that observer point of view, F equal to ma will be valid. F equal to ma will be valid if the observer is stationary or it is moving with a constant velocity. For the dynamics problem, we consider the inertial frame of reference, mostly the frame of reference which is attached to the earth. Even though the earth is moving, it is rotating. When it is rotating, it means it is accelerating. Since it is accelerating in the exact sense, the equation of F equal to ma will be invalid. But since the difference is negligible, the rotation of the earth, the angular velocity of the earth is very less. Due to this reason, the equation of motion F equal to ma is almost balanced. That is, there is little difference between F and ma. So since there is difference, there is insignificant difference, we can assume that the surface of earth is an inertial frame of reference. But still, if we want to have 100% exact results, we have to consider the acceleration components of the earth. We can study the effect of the earth rotation by a small example. Suppose there is a particle which is released from a certain height. When the particle will fall, it will move in the vertical direction. And in the ideal case, we suppose that object will strike the ground at the point which is exactly below the initial position of the particle. That is, the particle will fall in the vertical direction and it will strike the ground which is exactly below the initial position of the particle. But as the particle moves from top to bottom, the earth is rotating. When earth is rotating, it will not strike the point which is exactly below the initial position of the particle. There will be some horizontal shift, and that horizontal shift can be predicted by this equation. This relation was proposed by the earlier scientists, that when the earth is, for example, rotating, there is difference in the horizontal location. The exact location of the particle where it falls, and the location of the earth which was exactly below the initial position of the particle. In this equation, h is height, omega is angular velocity, and gamma is latitude. So as an example, we consider that the particle falls from a height of 200 meter and the latitude of any location is suppose 45 degree. The angular velocity of earth is 0.729 power 10 to the power minus 3. If we substitute in this equation, we get 0.044 meter, or it is 4.4 centimeter. So the object falls from a height of 200 meter, but there is a horizontal shift of 0.044. This means there is difference of 0.01%. So there is a horizontal shift of 0.01% when the object falls from a height to the surface of the earth. Now we consider the equations of motion for a system of particles. Previously we were considering only a single particle, but any object of the engineering application consists of a number of particles. Whether it is a solid, liquid or gas, there are several particles. We consider an ith particle and we show the forces. The ith particle has mass mi. It has internal forces due to the adjacent particles, and there are external forces. So internal force is due to adjacent or surrounding particles, and the external forces are gravitational force, electrical force, magnetic force and contact force. So external forces are the forces which are not due to the surrounding particles of the same object. For a single particle, we will write Fi, capital Fi plus small fi equal to mi ai. Small f is internal force, capital F is external force. We can see the diagram. This is a single particle within a system of particles, small fi, capital Fi. We add these two forces, internal plus all the internal forces. The vector sum will give the acceleration of a single particle. So this is a free body diagram, this is kinetic diagram. The position vector of this ith particle is Ri. From a fixed reference system, the position vector is small ri, and there is additional position vector which is of g. G is the center of mass. So rg is the position vector from reference frame to the center of mass. Now we consider the forces on all the particles. We consider all the particles together. So these are external forces on all the particles, and this is the internal forces on all the particles. But the internal forces cancel out, because one particle applies force on the other and the second one applies the force on the first one. So the internal forces will cancel out. The external forces will remain and it can result in acceleration. So we will write summation Fi equal to summation mi ai. From the previous figure we saw that Rg is the position vector and G is the representative location for the system of particles. For the entire object, the G is a reference location. So mRg will be equal to summation MI/RI. Here the summation is missing. So MI/RI summation will give M multiplied by Rg. M is the total mass of the object and Rg is the position vector to the center of mass. Mi is the mass of the particle and Ri is the position vector. So if we sum all the Mi/Ri, it will result in mRg, because some particle will be greater distance than Rg, some particle will be at less distance than Rg. So cumulatively we will get mRg equal to summation Mi/Ri. In the similar manner, we can write MAg equal to summation MI/AI. So we can write the equation of motion in terms of acceleration of the center of mass. So summation F equal to MAg.